So last time we talked about big guns, and we talked about the history of big guns and how they could be useful for getting stuff into space. But right now, we want to actually do a little bit of math to see how practical that actually is. TLDR, not super practical, but let's go through the math to see. So what we're going to do is we're going to consider a bunch of different problems, okay? So the first thing that we want to do is figure out how long does the gun launcher actually have to be in order to accelerate something up to orbital speeds, if the acceleration is limited to certain quantities. All right, so we're going to start off with something that is really outlandishly large, which is 1,000 Gs. That means things have to be extremely robust. Like normal electronics, like your cell phone or whatever, a normal satellite would not survive 1,000 Gs. That is just way too much. So you'd have to build things to be extremely robust to actually endure this. Next, we'll talk about 100 Gs, which is still pretty robust, but like a cell phone could actually survive this. If you dropped a cell phone on a cement sidewalk or something, then the electronics would survive that. You just have to sustain that force for a pretty long time. And some electronics can actually sustain that. At 10 Gs, normal satellites can survive this. This is pretty standard type of stuff for a normal satellite. On launches, they endure 10 Gs fairly often, or many satellites are designed to this. So it's not that bad. Humans are really sort of 10G is touch and go. You're going to black out for 10 Gs. You're going to die for 100 Gs, and you will definitely come nowhere close to surviving at 1,000 Gs. So let's look at 5 Gs, which humans can endure 5 Gs for a sustained amount of time. The next thing that we want to do is look at like what is the drag force that something would experience when it leaves the launcher. Because what's going to happen is that that gun launcher is going to accelerate something up to an orbital speed, and then it's going to come out of the gun launcher and it's going to be in normal air. And so it will start slowing down immediately. And it's going to have a very, very large drag force. So we're going to talk about that. And then we're going to talk about how much would that actually slow the object down. But the first thing that we need to do is we need to talk about how fast would something actually have to leave the launcher to make it to orbit. So let's talk about that math first. So the first thing we need to know is basically how fast does this thing need to be launching stuff at? Well, if you actually want to get to orbit, we could say it's at 400 kilometers, which is where the International Space Station is. We need to have two velocities. The first velocity is it's got to get up to 400 kilometers. So that's the vertical velocity. So if you were to shoot something straight up at 2,720 meters per second, it would go up to 400 kilometers and then it would come down. If you were, by some miracle, already at 400 kilometers and you shot something at 7,676 meters per second, it would orbit the Earth and it would stay in orbit. We need to combine those. So we shoot at sort of an angle. And then when we shoot at an angle at 8,144 meters per second, we will get to orbit. So 8,144 meters per second is what we're going for. That's what we have to design our big gun to do. What we're going to do is we're going to use what's called the kinematic equations. And the kinematic equations relate velocity, position, and acceleration. Okay? And they're just a way to give us, if we accelerate for some amount of time, what velocity do we get? Or if we move at some velocity for some amount of time, what position do we have? And so we're going to use these two equations that you see in front of you to do some calculations. The first thing that we're going to use is we're going to use the relationship between velocity, acceleration, and time, which is delta t, to basically derive delta t. Because we've got our velocity, we know that it's 8,144 meters per second. And we have an acceleration, which is 1,000 g's. And 1,000 g's is 1,000 times the acceleration of Earth, which is 9.8 meters per second. So when you multiply 1,000 times 9.8 meters per second, you get 9,800 meters per second. So if you take 8,144 meters per second and you divide by 9,800 meters per second squared, and we get 0.83 seconds. So in less than 1 second, accelerating at 1,000 Gs, we will be up to orbital speed. That is a fast gun. That is a very, very, very fast gun. So how long does the barrel have to be in that case? All right, so now we bring in equation 2. And equation 2 solves for delta x, which is basically the length. And that's equal to the initial velocity, which in our case is 0, times delta t, plus 1/2 times the acceleration times delta t squared. So when we plug in our numbers, we have 0 plus 1/2 times 9,800 meters per second squared, that's our acceleration, times our delta t squared, which is 0.83 squared. You plug in all of these numbers into your calculator, and we get 3,376 meters, which is 3.3 kilometers. So our super fast gun needs a barrel length that is 3.3 kilometers. That's 2 miles. It needs a barrel that is 2 miles long to do this acceleration. That's the fastest acceleration that we would ever want, really. All right, but now let's go to a slower acceleration, one that's actually sort of endurable by some electronic components. They have to be robust components. Humans can't survive it either, but it's still 100 Gs. So let's go to our equations. We're going to solve our equations for delta t first, exactly the same equation that we had before, same velocity as we had before, 8,144 meters per second. We divide that now instead by 100 times 9.8. And so we get 8,144 divided by 980, and that's 8.3 seconds. We plug that into our next equation, which is delta x is equal to v naught times delta t plus 1/2 at squared. So that's the velocity. The initial velocity is 0, so we just say that's 0. So we have 1/2 times 980 meters per second squared times 8.3 squared. You plug in all of those, that's 33,760 meters, and that is 33 kilometers long. That is very, very, very long. 33-kilometer barrel length of a gun. If we do the same thing instead of at 100 Gs, if we do 10 Gs, which, if you remember, is survivable by most satellites. Most satellites can endure that just fine. We plug in all of these numbers and do all of that math, and then we get 338 kilometers. That is like the width of a state in the United States. That's really long. That's really long. So now let's look at what it would take for a human. So humans can accelerate at like 5 Gs. And if they accelerated at 5 Gs, it would take about 166 seconds for the human to be accelerated up to this 8,144 meters per second. And it's exactly the same math as we have done before. We have this 8,144 divided by 49 meters per second squared now. We get 166 seconds. We plug in all of that math, and we get 675 kilometers. So you'd have to build a gun the entire length of Michigan to do this. So guns are not super practical for this. But let's say that you happened to build such a gun. All right. So what we want to do is we want to calculate the drag force when you leave that gun. You're traveling at 8,144 meters per second. And then as soon as you come out, you're going to start decelerating because you're going to hit the air and you're going to have this drag force. We can do this mathematically by using the drag force calculation. So that says the force of drag is equal to 1/2 times rho, which is the density of air. That's the mass density of air. And we're going to use the surface mass density. Then we use A, which is the area. And the area is basically like how big our rocket ship is. And as it's moving through the atmosphere, what is that area that's projecting into the air? And then we use this thing called the drag coefficient, which is CD. And that's basically like how well does air move around the rocket. And we're going to pretend that we have a really, really, really aerodynamic rocket. And then V is the velocity, and we're going to square the velocity. This is the drag force, and it is used for like calculating the force when you're riding your bicycle or calculating the force when you're driving a car. This is very standard thing to use. So we plug in some numbers that we know, and we're just sort of doing some assumptions. The drag coefficient we say is 0.1, which is very aerodynamic. And then the area, we're just going to say that the area is the radius of this thing is like 1 meter. And so we'll say that the area is pi, basically, which is 3.14. Rho, we're going to use, like I said, is the mass density of air, which is 1.29 kilograms per meter cubed. And that's just the surface mass density of air. And then the velocity that we're going to use, remember, we're going to try to go orbital velocity, right? So that's 8,144 meters per second. You square that, you multiply by the other terms here, and you get the force is around 13,400,000 newtons. That's a very large force. 1 newton is roughly a quarter pounder. So if we divide this thing by 4, we get how many pounds of force this is. So we divide 13 by 4 and we get roughly 3 million pounds of force. That's what this rocket will feel when it leaves the barrel. And this is why when rockets and stuff are re-entering the atmosphere and it's way, way, way up high, they're coming in and they're decelerating because of this drag force, and they're moving at like orbital velocities, and they're starting to feel all this drag force. And you see that there's lots of like burning air and stuff around them because this force is so large that it's literally causing the air to turn to plasma around it. All right. So this would be very, very, very bad for whatever thing was leaving the barrel. At 13 million newtons of force, it would start to vaporize the air very, very quickly. But let's pretend that this is what happens. Now, how much acceleration would you actually feel? So you're sitting in a rocket and you've just been accelerated up, and that was a nice, pleasant journey because it was only at 5 meters per second squared, or 5 Gs. And so that was hard to endure, but you got through it. As soon as you leave the barrel, you take this 13,400,000 newtons, you divide it by mass, because we're going to use F equals ma, and we can calculate A is equal to F divided by the mass. And we're going to make up a mass. The mass, we're going to say, is very, very large, because if it was smaller, it would be even more acceleration. So we're going to use a very heavy machine, a heavy rocket. We're going to call it 20,000 kilograms, which is about 50,000 pounds. When you do that, you come up with an acceleration that's 670 meters per second squared. We divide that 670 meters per second squared to put it into Gs, which is something that we can better understand. And then when we do that, we get that it's 68 Gs. And at 68 Gs, humans would die. They would be pancaked. That is the technical term. They would be flattened. So this is not very realistic at all. So then if we said, okay, that's a problem. So now what could we do? Like, how fast could we actually go if we wanted to make it so humans could survive leaving the barrel of the gun? Well, we could solve that problem too. We could solve all sorts of problems with math. So what we can do now, we say the maximum that humans want to experience is 5 Gs. We multiply by 9.8, and that is 49 meters per second squared. Now we say force is equal to mass times acceleration. We know our mass is 20,000 kilograms. We multiply that by 49, and we get 980,000 newtons. That is the maximum force that we can endure for our capsule at 5 Gs. So now we're going to take this 980,000 newtons, that's the force, and we're going to put it in the drag equation. Exact same drag equation that we just used on the previous slide, but this time we're not solving for the force, we have the force, and we're solving for the velocity here. We're going to use the same mass density, same area, same drag coefficient, and instead we'll solve for the velocity. So we take this velocity, we rearrange the equation, we get v squared equals to 2 times the force divided by rho a drag coefficient CD. We take the square root of that. So we get v is equal to the square root of 2 times the force divided by rho divided by a divided by CD. We plug in numbers here. 2 times 980,000 divide by 1.29, which is the mass density, 3.14, which is the area, and 0.1, which is the drag coefficient. When you do all of that math, plug that into your calculator, take the square root, you come up with 2,200 meters per second. So that is the maximum speed you can go. To have it when you leave the barrel, you'll be decelerating at 5 Gs. That 2,200 meters per second, if you remember to the first thing that I talked about, what velocity do you need to actually get up to 400 kilometers? And that is not even enough velocity to reach 400 kilometers. So we can't use a gun, a big gun, to basically get humans even up to 400 kilometers altitude. All right, big guns, not super practical. So let's summarize. So how long does the gun launcher have to be in order to accelerate something to orbital speed if the acceleration is limited to certain values? So at 1,000 Gs, which is extremely robust objects, extremely robust, it would have to be 3.3 kilometers or roughly 2 miles. At 100 Gs, which was still very robust, it would have to be 33.8 kilometers in length. At 10 Gs, which is sort of normal satellites, it's 338 kilometers, which is roughly about the width of Michigan. And then at 5 Gs, it would have to be 675 kilometers, which is roughly about the height of Michigan, roughly. And so that makes it very impractical to actually build a gun launcher. Then, if you were to build a gun launcher, what is the drag force that something would experience when it left the launcher? Well, that turns out to be 13,400,000 newtons. And that is enough force that it would basically vaporize the air around. Plasma would be created. It would be very, very, very bad. Then you could ask the question, what is the maximum speed for a gun launcher if you wanted to put humans on it and have them survive when it leaves the barrel? And we did the math on that. And that if we said that humans can endure about 5 Gs, the maximum speed that humans could go in a gun launcher is about 2,200 meters per second. And as soon as they leave the gun barrel, the drag force would slow them down at about 5 Gs. And that isn't enough speed to actually even get up to orbit at 400 kilometers altitude. And so gun barrels, gun launchers, are not super practical at this time, which is sad because they're a very cool concept, just not practical by any standards.